Hello everyone. In our last activity, our goal was to figure out a definition of a newton. In other words, what is a newton? Why is a newton the size that it is? And we did a lab where we were trying to figure out how much force it took in newtons to make a 1 kilogram cart accelerate at 1 meter per second squared. And if we look at the results that we got, many groups throughout the day, you can see that their forces were all pretty close to one another. In fact, on average, it was 0.995 or to 2 sig figs, 1.0. So it took basically 1 newton to make that 1 kilogram object accelerate at 1 meter per second squared. That's in fact how we defined a newton. And we said a newton is a kilogram meter per second squared. But that kind of begs the question, why? Why is 1 newton the force required to make a 1 kilogram object accelerate at 1 meter per second squared? Right? And for that, we need to know a little bit more about how force, mass, and acceleration relate to one another. And so that's the lab we're about to do. And this will be called Newton's second law when we're all said and done with it. And it is probably one of the most important math models in all of Newtonian mechanics. Without understanding this, it's almost impossible to understand why things move the way they do. But these 3 variables mean we're doing a 3-variable lab. Right? We haven't done one of those since our area of a triangle lab. So there's a couple of special things we have to remember about a 3-variable lab. That means we're going to have 2 independent variables and 1 dependent variable. Now remember, you can only change how many independent variables at a time? Only 1. Right? Because if you change 2 of them, you won't know which one's affecting the dependent variable. So since we have 2 independents, we're going to actually have to do 2 labs. One where we change one, and one where we change the other. Now when you're changing one independent variable, what should you do with the other one? Well, if you don't want it to affect things, you have to keep it constant the whole time. Right? So we need a fairly complex device in order to keep track of all 3 of these variables. Right? And you guys are going to do this with a Pivot Interactive of what's called a modified Atwood's machine. Right? A modified Atwood's machine has a mass hanging off the side, a string going around what essentially is a massless, frictionless, forgettable pulley, and that string runs to a cart. And when you let it go, right, it accelerates. Now with this, we're going to see all 3 of these variables. And so the purpose of this lab is to create graphical and mathematical representations of the relationship between the acceleration, the net force, and the mass. Okay, so those 3 variables. And all of them we can measure in here if we're clever. So let me show you, what this looks like, of course. When you hit start, when you've set your parameters and you hit start and you let it go, it's going to accelerate. See this mass falling and that cart accelerating? Now the only tools we need inside of this is a couple of things. First of all, down here is where you can choose a couple of things. Something called the hanging mass and something called the system mass, which we'll talk about in a little bit. Right? How much hanging mass and basically the total mass. Up here, you can get your tools. Right? And there's a horizontal ruler and a stopwatch. You're going to use the horizontal ruler and put it up here on the track to figure out the displacement the cart goes. And then you're going to use the stopwatch to figure out how long it takes. Because with displacement and time, you can calculate acceleration. And I'll go through that a little more fully here as we go. So, in our first part of the lab, because remember we have to do 2 labs, part 1, you're going to control the net force and change the net force, and then measure the resulting acceleration while keeping the total mass constant. Okay? That's first half of the lab. We'll do the second half of the lab tomorrow. So, here's our modified Atwood's machine. Okay? And I'm going to use this as a system diagram. Okay? I'm going to look at this as one big object, right, instead of as 2 objects tied together by a string. Remember doing this a couple of units ago? So if I pull B up next to A and kind of forget about the tension in the string and the pulley in the whole thing, because that's now inside, right? Little dotted line is our system diagram, right? Our system line, if you will, boundary. So we're going to call M sub A the cart mass. we're going to call m sub b the hanging mass, right? Hanging mass. And then the two of them together is a system mass. Right? If you remember, you can control the hanging mass and the system mass, right, in the video. You can choose different hanging masses and different system masses. Right? This lab, the cart mass is just part of the system mass. Okay? So let's do a little force diagram, and then that'll help us decide how we're going to use these things to do the lab. So what forces act on our system of two objects? Well, gravity. In fact, two gravities. There's a force of gravity acting down on object A, which I will call F of G A. There's also one acting on B. Now, in real life, that acts down as well. But we pulled this mass up next to A. So you remember the direction we draw it? Yeah, we draw it on the diagram out to the right. Okay? It becomes, if you will, the towing force, the force that's making everything move here. Cart A, notice F of G B, because it's the hanging mass. Cart A is supported by the track, so there'll be an upward normal force. And that will balance out F of GA. How do we know those balance? Because what's it not doing vertically? It's not accelerating. It's got a constant velocity, but remember we can use our new terminology and say it's not accelerating. So, what's causing the net force, or what is the net force in this case? Well, look at our force diagram, right? We've got three forces, but these two balance out. So that means the net force must be F of GB. Now, remember, we're neglecting the tension and the strings are in here. We don't need those when we look at it as a system. That's the advantage. Right? So it's F of GB. And can we figure out the force of gravity acting on B, or the weight of B? Sure we can, because we have a math model to calculate F of G. Right? So in this lab, the net force will be the force of gravity on the hanging mass, which will be mg. The hanging mass times the gravitational field strength. Now remember, since the gravitational field strength is 9.8 newtons per kilogram, we need our hanging mass to be in kilograms. The video uses grams. You've got to convert for your lab sheet so that you can calculate this. Okay? So note, if we change the hanging mass, we'll have changed F of GB, which means we'll have changed the net force. So this is just saying, hey, you've got to set the hanging mass and the system mass by using the parameter selection panel at the bottom of the video. Now in this part of the lab, we want the system mass to be constant, the total mass here to be constant, right? So you can set that, right? I would like you to set it at 400 grams, which is 0.400 kilograms. So in part one, every trial, leave the system mass at this, okay? The cool thing about the way it's set up then is when it changes the hanging mass, it also changes this mass, the cart mass, so that the total stays the same. And it does it for you. Okay, so you don't have to do anything fancy. You just have to choose them. With me? Now, when you set a new set of parameters, you have to press load. Okay, if you don't press load, it doesn't load up the new video. All right? So if you don't do that, you keep seeing the same video over and over and over again. By the way, all of these instructions are on your lab sheet, right, which you can print off the schedule doc. Very written out with buttons and everything. Okay? So that's how we're going to control the net force. How are we going to measure the acceleration? Well, as I said, we can put a ruler on there to measure a displacement, how far it goes. In fact, I've told you how far to use, 40 centimeters, 0.40 meters. Right? And then we can use the stopwatch to measure the time. If you've forgotten how to do that, well, that's okay. There are some instructions on your lab sheet. Once you have the displacement and the time, you can calculate an acceleration using the third kinematic equation, because this thing is accelerating uniformly. Since the forces are constant, the acceleration is constant. Here is the third kinematic equation. Since it starts at rest, VO is 0 and 0 times t is 0, so that whole thing drops out. And if we do a couple of steps of algebra, we can solve for the acceleration. Right? Multiply by 2, divide by t squared, and we get this equation. So once you measure inside of the video, right, following the instructions, the displacement and the time it takes to go that displacement, you can plug them into this equation and calculate the acceleration. right? And that's how we're going to get away from having something fancier like in class where they're going to use this special cart that has an encoder wheel and the computer keeps track of the turning of the wheel to figure out how far it's gone, all right? Kind of fancy. For us, we're going to measure displacements in time inside of the Pivot Interactive. It actually works really well if you're careful, okay? So this is how we are going to do the first half of the lab. Once you get data for acceleration for a bunch of different net forces with constant mass, remember we control the net force by controlling the hanging mass. Right? Then you're going to go and follow the lab sheet instructions. You're going to make a graph and graphical analysis and a linear fit and all that good stuff and slopes and y-intercepts and math models and all that good stuff. Right? So do that on the lab sheet and finish up that lab sheet. Then you have to go back into Pivot and answer a multiple choice question about the slope of your graph. Okay? But that's the last thing you do to finish up that half of the Pivot. Okay? There is a second part to the Pivot, but that's part 2 of the lab. We'll talk about that tomorrow.